Right, here we finally are with our study of trigonometry. In a way, this is where everything is led in this class. Most of what we have done has been about the relationship between side lengths and angle measures and triangles. And trigonometry is really the final chapter in that story. It allows us to definitively answer what is that relationship. Um, and just to prove to you that that's really what we've been on about for the most part, consider some of the landmark theorems we've proven. Like, for instance, the isosceles triangle theorem, which says that if a triangle has two equal sides, then the two equal sides, then the angles opposite are equal. Obviously, relationship between side lengths and angle measures, or congruence. Side congruence, for instance, that it says that if we have two triangles with equal sides, then they must have equal angles. So we have these two systems of measure. We have length measure, side length measure, and we have angle measure. And this class has been primarily an investigation of the relationship between them in triangles in particular. And it is really trigonometry that provides the final answer to what this relationship is. All right, so let's do some trig. Now, before we do the trig, we have to get familiar with a pair of terms, that is opposite leg and adjacent leg. Because what'll happen is this, is we'll be in a right triangle, and we'll have to form ratios of side lengths. And that ratio will depend upon what is adjacent to us and what is opposite to us from a certain point of view. So in particular, let's say that we're at one of the acute angles in a right triangle. So in the one that's shown, right triangle ABC with its right angle at C, let us say that we are at the vertex of acute angle A. Then one of the legs is the leg adjacent to us, the one that's right there next to us, that's B, and the other is the one that lies on the opposite side of the triangle, which is A. But let us say that we get up from vertex A and go instead to vertex B, then what's opposite and adjacent changes. The adjacent leg, the one that's next to us, is now A, and the one that's opposite is now B. Do note that when we talk about opposite and adjacent, that's always short for opposite leg and adjacent leg. And these are always judged relative to the vertex or the point of view of one of the acute angles of a triangle, right triangle. All right, so now we can go on to the definitions of sine and cosine and tangent now that we understand how opposite or adjacent are used. All right, so let's say that alpha is the measure of one of the acute angles of a right triangle. Sorry, I want to get my pen. So that's the alpha right there. First letter of the Greek alphabet, often used for angle measures and triangles. And again, let us say that it is the measure of an acute angle of a right triangle. Okay. Now the sine of alpha, abbreviated SIN alpha, is the ratio of opposite leg to hypotenuse. And let's pause and think about what's been said here. There's like an input and an output to this. There's what we take the sine of, that's the input, and then there's what the sine of it is, and that's the output. So what we take the sine of is the acute angle measure here called alpha. And the output is a ratio, okay? The output is a ratio. What ratio is that? It is the ratio of opposite leg to hypotenuse from the point of view of angle alpha. Okay, and we'll see a picture in just a second. Now for the definition of cosine. Once again, it's the cosine of an angle as the sine was sine of an angle. That's its input. And the output is once again a ratio, but the ratio is different. For an acute angle alpha, the output of the cosine function is the ratio of the adjacent leg to the hypotenuse. And finally, the tangent of alpha, input alpha, is once again a ratio, but also once again a different ratio. It's the ratio of the opposite leg to the adjacent leg. Okay, so notice the similarity between all of these, right? In each case, we have a function of um, an acute angle of a triangle, and the output of that will always be a ratio of side lengths. Okay, and what that ratio is depends upon the particular trigonometric function involved. Oh, and one small point before we go on, and I'll give you a way to remember all this and show you a picture. But a point about pronunciation. The full name of the sine function is spelled S-I-N-E and cosine C-O-S-I-N-E and tangent, as you see. But we do often abbreviate them, right? So SIN for the abbreviation of sine, COS abbreviation for cosine, TAN abbreviation for tangent. And though those are the abbreviations, and that's what you'll most commonly see as the names of these functions, they are still pronounced just as the unabbreviated form is pronounced. So SIN is not pronounced sin. This is not a biblical inquiry; it's a trigonometric one. Even though it's spelled sin, it is pronounced sine. And cos is pronounced cosine, and tan is pronounced tangent. It is not tan. All right, so here's a way to remember the definitions of sine and cosine and tangent. It is like the classic way to do that. It's the mnemonic device SOHCAHTOA. That is, it's a sequence of sounds that helps you to remember. It encodes information. And I do believe, this has always been my experience, that if you say aloud to yourself SOHCAHTOA a few times, you'll maybe never forget it again. I've had discussions with adults whose trigonometry was many decades in the past, and they still remembered SOHCAHTOA. Anyway, so say it a few times, SOHCAHTOA. But it's spelled as you see up at the top, SOHCAHTOA. Now, what does that do for you? That encodes the definitions of sine and cosine and a tangent. Okay, so look at the first part, the SOH. What that says is that sine is opposite over hypotenuse. The S is for sine, the O is for opposite, and the H is for hypotenuse. So if you can remember the sound so, you also remember the definition of sine. And then ka, the C is for cosine, the A is adjacent, the H is hypotenuse. So that tells us that cosine is adjacent over hypotenuse. And then, of course, toa, a tangent, the T for tangent, the O for opposite, and the A for adjacent. So tangent is opposite over adjacent. And very often, what I'll have students do on their trigonometry test is that when they first get it, they'll write simply the letters SOHCAHTOA at the top of their test, and then they can refer back to it if they need to and pull out the definitions of sine and cosine and tangent. It works. All right, so let's make sure that you understand what all this really means. You can say the words, but of course you need to know what this corresponds to in diagrams of right triangles. So we have a right triangle with acute angle measures alpha and beta. Leg links A and B, where A is opposite alpha, B is opposite beta, and hypotenuse links C. And then what we wish to do is to write the sine, cosine, and tangent of each of alpha and beta. Okay, so the alpha and the beta, that's like the input to the function, okay? And what, again, is the output? Well, in every case, the output is a ratio. And what ratio it is depends upon the particular trigonometric function involved. And if you don't remember, and if this is your first introduction to trigonometry, you probably don't, here is that mnemonic device that you can pull the definitions out of. So sine of alpha. Well, sine is opposite over hypotenuse. That's the SO. And from the point of view of alpha, the opposite is the length A, and the hypotenuse is length C. So the sine of alpha is A over C. So what's the cosine of alpha? Well, cosine is adjacent over hypotenuse. From the point of view of alpha, the adjacent is B, and the hypotenuse is still C, so that's B over C. And now the tangent of alpha. Tangent is opposite leg over adjacent leg. From the point of view of alpha, the opposite leg is A, the adjacent leg is B, so this is A over B. All right, now let's get up from alpha and move to beta and form our ratios from that point of view. So sine of beta, sine still opposite over hypotenuse. From the point of view of beta, the opposite is B, hypotenuse is C, so we get B over C. The cosine of beta, that's adjacent over hypotenuse, which is now A over C. And tangent of beta is opposite over adjacent, which is B over A. Now, when you get to your pre-calculus class, you will have an entire almost half semester devoted to the study of trigonometry. And part of that will be the set of relationships between the sine, cosine, and tangent functions and other trigonometric functions as well. But even with what little we've done, you can begin to see relationships between them. Okay, so for instance, look at the sine of alpha, which was A over C, and the cosine of beta, which is A over C. They're the same. But when you reflect, this should come as absolutely no surprise at all. Because when we get up from alpha and go to beta, what's opposite and adjacent flip. but sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. So since opposite became adjacent, as we went from alpha to beta, the sine and the cosine have to be the same. Or for instance, there are many relationships here. Here's another one. Consider the relationship between the tangent of alpha and the tangent of beta. You might know to call those reciprocals of one another. One is a ratio and the other is that ratio flipped. And that should be no surprise because tangent in both cases is opposite over adjacent. But as we went from alpha to beta, what was opposite became adjacent, and what was adjacent became opposite. So of course we get the reciprocal, right? So that's absolutely no surprise at all. All right. So before we move on and begin to do a little bit of calculation with the trigonometric functions, let us ask and then answer a mandatory question. Okay. So an assumption that is run throughout the work that we've done so far is that, well, it seems not to matter which right triangle we're in that has a measure of alpha, whatever that is, right? We just talked about the sine, and that sine seems in no way to depend upon which triangle this is, where it is, what its size is. And that is true. Okay, the value of the cosine or the sine or the tangent of a particular acute angle of a right triangle depends only upon that angle measure. Okay, nothing else is needed to know what the ratio is, like in the case of sine, opposite over hypotenuse. But we need to understand why that is the case. That is, we need to understand why it is, for instance, the value of the sine of an angle is the same in all right triangles that have that angle measure. Okay. Well, let's take a look at a picture. And I think with the picture, it'll begin to become clear why this is true. Okay, so we have a right triangle on the left with side lengths A and B and C, and one on the right with side lengths R and S and T, and they both have an acute angle of measure alpha. Of course, in the one on the left, we would say that the sine of alpha is opposite over hypotenuse, which is B over C. And on the right-hand side, the sine of alpha would be S over T. But again, our assumption here is that that value will be the same. It doesn't depend upon where the triangle is or what size it is. And we want to understand why that is the case. Okay, well, let me ask you, what is the relationship between these two triangles? Well, of course, alpha in one equals alpha in the other, and the right angle in one is equal to the right angle in the other. So by angle similarity, these triangles are similar to one another. Okay, which means that the ratios of sides that correspond are equal. That's, of course, the proportionality of sides that correspond. But look at what sine of alpha is on the left. It is a ratio. Look at what sine of alpha is on the right. It is a ratio. And these two ratios are ratios of sides that correspond. So, of course, then by angle similarity, the sine of alpha on the left is equal to the sine of alpha on the right. So that fundamental assumption that's made in trigonometry, that you'll get the same value for the sine or the cosine, the sine, cosine, or tangent function, no matter how big or small or where your triangle is. Ultimately, that depends upon angle similarity. Angle similarity lies at the foundation of trigonometry and makes it possible. All right, so there's something that I want to look at with you. I'll call it a gift. Also, the table of the gods. Now, what it will be is this, is it will be the values of the sine and the cosine and the tangent functions for whole angle measures between 0 and 90 degrees. And we'll look at it. I've got just a bit of it on the next slide. And a very good question will be, where do these values come from that we're about to see? And honestly, though it pains me to say this, this is beyond us. This is beyond our capability. It is an old and important question in the history of geometry. It goes all the way back to Euclid and before, how actually one gets these values that we're about to see. And there was much work done historically in trigonometry to find these values. They were tables like the one we're about to see. But ultimately, from a modern point of view, the way that one answers this question is with the tools provided by calculus, a class that you have not been in yet. So formula from the calculus together with computers that enable us to do fast computations give us the values that we're about to see in the table. Okay, so let us just simply take it as a gift. But even though we cannot derive these values ourselves, in most cases anyway, we can certainly understand what it means. Okay, so here's a bit of that table, okay, that gift that I give you, the table of the gods. Now, there is on my website a link to the entire table, and I'll also give you a link at it. You might notice that it only goes down to, let's see, on one side 26 and on the other side 72 degrees. that's because I didn't want it to be just tiny. But we've got enough of the table to certainly understand what it is. Okay, so first of all, you'll notice that there's a radian column. Ignore it. That's another way to measure angles. It's another unit of angle measure. We will not use it in this class. This is a degree class. So we're only concerned with degrees. Okay. And notice that we also have a sine and a cosine and a tangent column. Now, let's pick a particular angle measure. Okay, so let's pick like 18 degrees. There it is, I circled it. Okay, so what one would do is one would travel to the right from that 18-degree measure, and one would see the values, one would find the values in the columns underneath. So the 0.309 is under the sine column, the 0.951 is under the cosine column, the 0.325 is under the tangent column. And so what that means is that the sine of 18 degrees is 0.309, the cosine is 0.951, the tangent is 0.325. And we know the significance of this, okay? When we talk about the sine of 18 degrees, for instance, we are in a right triangle. We are at the acute angle that measures 18 degrees. And the sine is, from the point of view of that 18-degree angle, the ratio of the opposite leg to the hypotenuse. So that's what the 0.309 is, okay? So if one is in a right triangle with an 18-degree acute angle, the ratio of the opposite leg to the hypotenuse is 0.309. The ratio of the adjacent leg to the hypotenuse is 0.951. And the ratio of the opposite leg to the adjacent leg is 0.325. Okay, so even though you'll see on some later worksheets that a few of these values we can get ourselves, but most of them we cannot. But though we cannot get most of these values ourselves, we understand their significance. We understand what they mean, which for us is really what's most important. Okay, so what does this table allow us to do? Well, it allows us to solve problems like the one that you see in front of you, which we would not have been able to do before. If before this section I had asked you to find the values of x and y, the best that you could have done, I think, was to write x squared plus y squared equals 32 squared. That's, of course, an application of the Pythagorean theorem. But that equation contains two variables, and you cannot solve for either one of them. So it seems like you would have been stuck. But now we can do better. We can actually solve for the values of x and y, okay? And we'll do that with the trigonometric function. So here we go, okay? So I'm going to use sine, and you'll see why, okay? So of what do we take the sine? Always the acute angle of a right triangle. Okay, so let's use that 72-degree angle. And what does that output? That is, what is the sine of an acute angle? It's the ratio of the opposite leg to the hypotenuse. From the point of view of the 72-degree angle, the opposite leg is the y, and the hypotenuse is the 32. So here's our definition based on the definition of sine. The sine of 72 degrees is y over 32. And if we do just a bit of algebra to that, we get y is 32 times the sine of 72 degrees. And then what will we do with that? Well, we'd hop back to the table. We'd find the sine of 72 degrees, which is 0.951. We take that back. So 32 times 0.0951. And then we'd multiply that out with the help of a calculator, and we'd get what the result is. I should note that this answer will only be approximate. Most of the values in this table are actually irrational quantities. So for the most part, we only get approximations, but we'll mostly ignore that. All right, so let's say that we wanted to get x. Well, what would we do? Well, let's try cosine. So cosine of 72 degrees is by adjacent. Oh, let me remind you, sine is opposite over adjacent. Cosine is it's opposite over hypotenuse. Cosine is adjacent over hypotenuse. That's the so and the ca. So if we do the cosine of 72 degrees, that'll be the adjacent x over the hypotenuse 32, which, if we do a little bit of algebra, means that x is 32 times the cosine of 72 degrees. And we can do what we did before. We can hop back to the table, look up the cosine of 72 degrees, which is 0.309, hop back over, plug that in, and then find the value of x. All right, so here's another example, and I'm not going to go all the way through this. Let's just find, for instance, the value of x, and I'll talk about two ways that one might do this. You can make your choice. Let's see, if one wanted to get x, then I think one would need to use tangent, because we need to make use of that 15, that known quantity, but that's the opposite leg, and the x is the adjacent leg, so we need a trigonometric function that involves opposite leg and adjacent leg, and that's tangent, TOA. right? So we would have the tangent of 36 degrees is equal to 15 over x. Let me erase that out. 15 over x. And then let's make sure you can do the algebra. Sometimes students don't do this right. So to solve for x, we would multiply both sides by x, which I just did. So I get x times the tangent of 36 degrees is equal to 15 because x over x is 1. And then I would divide both sides by the tangent of 36. And we'll do a table lookup in just a second to get the value of tangent 36, but I'll just write it like that for now. Tangent 36 over tangent 36 is 1. That's some quantity over itself. So we get that x is 15 over the tangent of 36 degrees. And once again, what you would do is you would hop back to the table and you would get the tangent of 36 degrees, and it's not there in the table, so I can't pull it off right now. But one could. You'll have the complete table and then plug it in and you'll get the value of x. Okay. Now, just to point this out, one could also, of course, easily find the measure of the other acute angle. Oh, excuse me, it's not 44 degrees. I can't do basic arithmetic sometimes. It will need to be 54 degrees. So one could find the measure of the other acute angle, which is 54 degrees, and one could work with that, right? So for instance, one might have said instead of tangent 36 is 15 over x, one might have gone the tangent of 54 degrees is x over 15. And the final answer that you would get would be precisely the same. All right, so that is our introduction to trigonometry. Oops. Oh, sorry, there's one other little bit that I want to do. Let's make sure, I'm not going to solve this one out, but let's make sure that you can translate this like English language description of a triangle into a diagram. And this is already something that we've talked about, but I will do this very commonly, and I just wanted to make sure you know how this works. So we've got a triangle ABC with its right angle at C. I've just drawn that. Little b is 12. Little b is opposite big B, so there's where the 12 is. And big A is 42 degrees. And we wish to find A and C. Where's little a? Opposite big A. Where's little c? Opposite big C. Of course, that's the hypotenuse. And then now we have a triangle like the one that I showed in the previous two slides, and you can do trig and you can get the values for A and C.